Yeah. It's February 16th. We're doing our Thursday night tube guitar amplifier webinar session for newbies. And we're going to start off by just kind of reviewing a little bit of what we talked about up until this point. And what I've got here is a drawing on your screen of a resistance capacitance coupled triode amplifier. You're going to see this circuit over and over and over and over again in every amp just practically every amp you ever see. I'm sure it's going to be in every amp you ever see, because this is the circuit this is your basic tube circuit that's used over and over again. Now the same circuit is used on the preamp or the output stage, but usually on the output stage, always on the output stage, it's transformer coupled instead of resistance coupled. And the reason for that is because of the impedance. Tubes are high impedance, so you can resistance couple them. Speakers are low impedance, so they have to have a transformer because it has to go down so low. And we're going to cover a little bit more of that later. But just briefly, let's go over the what we talked about in the past. And to keep this simple, I'm going to take this and I'm going to cut this off right here. And we're just going to move this out of the way. And we're just going to look at the very first section here, this right here. Now, of course, the way this is drawn, it could be connected to an input jack here. It could be connected to a previous stage. It could be connected to a reverb pan. But this is connected to something. It's either connected to your guitar pickup or another stage. But this is like the input of the tube, so to speak, or the input of the amplifier. And if we put a jack here, and you plugged into it, then your guitar pickup would be connected to this one resistor right here. And, go through the pickup, through the resistor, and then when the current would go the other way, it would go this way. So it's a rotating circuit, just like the word circuit. And, but it's going back and forth the same frequency that your guitar string is vibrating. And when this happens, it's going back and forth like this. When it happens, the voltage right here on the top of this resistor is going to either become more positive or less positive. Because when you're running an AC voltage through here, just think of water going through a kink in a hose. You got water coming in, it hits a kink. This resistor here, let's think of that as a kink in the hose. When the water hits the kink, it's going to build the pressure up right here. So this pressure right here is going to be high. And then after the water goes through the kink, this pressure here is going to be low. So high, low. But then when it goes the other way, when the current goes this way, then the pressure here will be high and the pressure here will be low. So what you've got is the top of this resistor, the pressure, which is voltage, the pressure, it's going to go a little bit higher, a little bit lower, but it's going to do it at the exact same frequency as your guitar string is vibrating. If you're playing an A440, this is going back and forth 440 times in 1 second. Now, the top of this resistor, by the way, this is the only resistor that your guitar signal goes into the amp. You got that one resistor and that's it. And there is no more guitar signal for the whole rest of the amp. We call them an amplifier. It's not really an amplifier. What it is a power supply modulator. And the only thing that we're doing is we're modulating with this one resistor here, but everything else after that's power supply. And we're going to look at the power supply section here. Let's see here. Let me switch this back. Well, let's see. I can get it back easier like that. There you go. Okay, so we're switching that back. So now we've looked at that part. Now, I don't want to look at this other part over here for right now. Let's don't look at this. Let's move this out of the way. And the next part I want to look at, this is another circuit or circle. You got actually 3 circuits here, 3 circles. One is your input that we talked about going to your guitar pickup. The next one is you got a power supply hooked to a tube. So this power supply is hooked to this tube, and you have one side of this power supply. We're drawing it as a battery here, but it could be any power supply. It could be a battery. It could be a power supply like what's in a guitar amp. But anyway, the electrons are coming up from ground. Here's ground. They're coming up from ground. They're going through this tube. They're going through this plate, and they're coming back to this voltage here. And they're doing this, and this is not alternating current. This is not alternating current. This current's always going one way. So this is DC current. See, that's different than your guitar pickup. Your guitar pickup is alternating current because it goes both ways. This is DC current. It's only going one way, and it can only go this way. And because you've got current coming up, boiling off of this cathode going to this plate. But the thing is the cathode's negative because it's connected to ground, and this plate is positive because it's connected ultimately to the positive side of this power supply. So just like opposites attract, your negative electrons are trying to get to that positive plate. Negative going to positive and going around in a circle like this. But there's only one thing. This grid here, which is just a very low mass type of screen. It's a grid. It has a lot of holes in it. This grid is connected to the top of this resistor. So as this top of this resistor is changing to more plus and more minus and more plus and more minus and more plus and more minus at the same frequency as your guitar string is vibrating, then the top of this grid is changing charge. Now there is no current. This is very important. There is no current flowing from this grid to this plate. There's no current. The only current you have flowing is from the cathode to the plate. What you've got this grid in here for is just for the charge. Because as this grid becomes more negative, then these negative electrons are not as attracted to that positive plate as they were a moment ago, because now you've got a little bit more negative in there, and so it's not as positive, is the way this cathode looks at it. So not as much current flows when this grid is negative. When this grid is less negative, or in other words, more positive, then these electrons here are going to go to the plate because they're going to not be repulsed. If this grid's negative, they're repulsed a little bit because they're negative, and two negatives repulse each other. But when this is more positive, then the electrons will go right on through, and they're not going to stop on the grid because the grid is not that positive. It's like 1 volt or so, and the plate's like, maybe 200 volts. Actually, the grid's not even 1 volt. It might be 1/8 of a volt or 1/4 of a volt at the most. This plate is what's real high voltage, like 200 volts. So that negative is going to go towards that plate. However, it's not going to always be smooth because as this grid is changing back and forth, it's changing the amount that's going to go at any given moment from cathode to plate. So what you've got here is red, pulsing DC. It's pulsing. Why is it pulsing? Because as this grid is turning the tube off and on, turning it off and on, it's making this pulse. But it's all going one way. So it's pulsating DC. Now, is everybody with me on that circuit? Because that's the second circuit. Let's see here. If anybody has a question or something, you can stop me anytime. Just raise your hand. I'm going to look at this. I really do want you to ask a question if you're not clear, because somebody else might be having the same question in their mind. And you might as well, let's go ahead and let's talk about it. Okay, so anyway, so this current's going faster or slower. Now, ignore this resistor capacitor thing here for right now. Just ignore that. And let's look at this resistor over here. As more current wants to flow through here, you're going to get a voltage drop across this resistor. Now, a voltage drop is just a change in pressure, because if you've got a lot of current trying to get through here and the pressure is high here as compared to here, then that's not the same as if there's a very little current going through here and now the pressure here is different than it was a moment ago. Let me put it another way. Let's get real technical here. We're even going to use a little math, maybe. We'll use some math. Okay. This resistor is usually, in most all amps that you'll ever see, it's either going to be 100K, sometimes it's 200K, 220K. And some of the vintage amps maybe 250K, but almost all the amps it's 100K. 100K. And let's say that this power supply here is doing 300 volts. Okay, so you got 300 volts there. And this tube, we don't want it to be completely off. We don't want it to be completely on. We want it to idle somewhere in between completely on and completely off. So that's why we have this R2 over here. This causes a slight voltage drop across this resistor, usually around 1.5 volts. And usually this R2 is usually 1500 ohms, which is way, way less than this resistor over here. Now, the tube draws approximately 1 milliamp. So when you do your Ohm's law and you run 1 milliamp of current through this R2, and R2 is a 1500 ohm resistor, it works out to 1.5 volts. So you have 1.5 volts positive here. So at this point, the tube thinks that the grid is 1.5 volts more positive than it is, and that's what idles the tube halfway between all the way on and all the way off. If you didn't have this there, then the tube could be all the way on all the time, and the grid would just make it cut off some. You don't want that. You want it to be, where that grid is keeping the current right in the middle of all the way on and all the way off, so that the waveform will have a place to take place in. So anyway, that 1 milliamp of current goes through here. And when the 1 milliamp goes through R3, if you do your Ohm's law and do the math, it works out to R3 is going to have approximately a 100 volt drop, because 1 milliamp times 100K is 100 volts. So there we go. So you got 100 volts here. So that means if you've got 300 volts over here, and this resistor is dropping at 100 volts, then what we're going to have is 200 volts on the plate. And that is with the tube idling. Well, as this grid goes more positive and less positive, it's going to make this voltage fluctuate, because you're going to have more or less current going through this resistor. If you got more current going through the resistor, you're going to have a bigger voltage drop. That bigger drop is going to be subtracted from this 300, which is going to leave less than 200 over here on the plate. And when the current swings the other way, and you have less current going through here than the 1 milliamp, then this 100 volt will go down, because you have less current going through there. So, let's say it goes down to 50 volts. Well, if it goes down to 50 volts, and you still have your 300 volt supply, that's going to make the plate voltage go up to 250. So this plate voltage is constantly going up and down. And the reason it's going up and down is because you're running current through this resistor here. Now, and that's where your third section comes into play. Your third section is the coupling. This is what makes it RC coupled, this right here, this circuit. And the way this is working is, as we talked about, opposites attract. So this plate right here, this conductor side of the C2, this voltage is constantly going more positive, more negative, less positive. It's going from maybe 200 volts to 250, down to 150, back to 250. It's going all over the place, but it's always positive. So what happens is electrons will come up from ground to try to get to that. Now they can't get to it because a capacitor is two conductors separated by a non-conductor. So there's a non-conductor between this conductor and the other conductor, but they're close enough that the electrons will try for it anyway. So they're going to go up and they're going to try to get to that positive voltage, and they're going to get right here and they're going to stop. And then a moment later, this voltage here changes and it goes down. So now it's not as positive as it was before. And so some of these electrons are repelled and they go back down here. And then it changes again and they come back up and back and forth at the same frequency as the guitar string is vibrating. You see? And so now we have AC again. You started off with AC. The middle section showed pulsating DC, and now we're back to AC again. But this AC is much bigger than the original guitar signal, which is why they call it amplifying. But like I said, we're really just modulating the power supply. Okay, so this is like a recap of what we talked about last week, and I'm going to pause before I go on. We're going to pause and see if anybody has any other questions or comments. Raise your hand, please, if you have a question or comment. Andrew D'Angelo. Talk to me, Andrew. You got your microphone muted, Andrew. You're going to have to unmute it.
Is this the same as biasing in this circuit?
Say that one more time.
Is this the same as biasing in the circuit when you are controlling the power that's going through the cathode to the plate?
Okay, biasing. No, this is not biasing. This is just shows you how an amplifier works. The biasing, there is some biasing going on, and it's going on with R2 over here. Right here, R2. And the way that it's biased, it's like this. Let me get a clean sheet of paper here, and I'm going to draw this out for you. Well, heck, I know I got it right there. Okay. Let's say we're going to make a little graph here. And this is just going to be 0. We'll let that be 0. And then this right here is going to be saturation. You know what? Let me redraw that. I can do better than that. Okay. Let's say this right here is just 0. It's nothing. This right here is the most current that a tube can draw. Because you can take that grid and start making it less negative and more positive, and it'll draw more current. And if you keep doing that and make it more and more positive, you'll get to a point where it's drawing as much current as it can possibly draw. It's never going to draw any more current than that. It's like a faucet that's wide open. Well, that's what we call saturation. But then if you started making that grid negative, you could make it negative enough to where all the current would stop, and we would call that cutoff. So the area that we have to work with now is just this area between cutoff and saturation. So what we want the tube to idle at is 0. Because if it's idle at 0 and you hit your guitar string, the guitar string is going to go positive a little bit. It's going to go negative a little bit, positive a little bit, negative a little bit. And there'll be a place for the waveform to occur. So you want that 0 point to be in between saturation and cutoff. Well, on a 12AX7, which almost all amps nowadays use 12AX7s for preamp tubes, and a lot of the vintage amps did too. Most of the Fenders did. A lot of the British amps. I mean, it's a very popular tube. To make this idle, this grid needs to be more negative than the cathode. And, you know, back in the old days, one of the things they would do is take R1 over here and instead of ground it, put a little battery right here. They put a little battery in there, right here. Put a battery and then have the negative facing up. And that way there would always be a minus 1.5 volts on this grid. And the battery would last forever because it wasn't drawing any current. It's not going anywhere. And that would be one way of biasing it. And then you have your cathode going to ground. But that's a hassle because then you'd have to change the batteries every year or so. And it's just a hassle. So what everyone does, instead of doing that, is they put a resistor over here. And when current comes up to this resistor, you're going to get some voltage over here, let's say 1.5 volts, positive. But there's no current going from this grid through this resistor to ground. So this grid is at ground potential, which is 0. So now, with the cathode at 1.5 volts and the grid at 0, the tube still sees the grid as being 1.5 volts more negative than the cathode. And that's what biases the tube on a 12AX7. In other words, if you put that grid at minus 1.5 volts by comparison to the cathode, then the tube is going to idle right about halfway between cutoff and saturation. And you could say that that voltage difference between the grid and the cathode is bias. Matter of fact, you can always check the bias of a tube, any tube, by taking a meter and putting one end on the grid and the other end on the cathode and see what the difference is in voltage. Whatever that difference is in voltage is your bias voltage. Okay. Let's see. Okay, somebody had a question about DC output. What's the difference between a capacitor and a diode? And we're going to cover that in a minute. Is the battery in the diagram also known as B plus voltage? Yes. This right here would be your B plus power. B plus is this power. The heaters, which I'm not showing in this because there would be a heater underneath this cathode and it'd be connected to another battery or another supply. And a 12AX7, even though it's a 12.6 volt filament in there, it is center tapped, so most people wire them 6.3 volts using the center tap and then put the ends together for the other side, and that way they're humbucking. We don't show it, but that would be called your A supply. Your filament is your A supply. The plate of the tube is the B plus supply. And C minus would be if we were going to use a negative bias on the grid, a negative bias supply, we'd put that negative bias supply here and it'd be called a C minus supply. So that would answer that question. And we're going to look at the diode. Daniel, we're going to look at the diode and capacitor thing here in a minute. Okay. So any questions on anything we've covered so far on this review? Robert Perkins.
No, actually, I'm good.
What's that?
I'm good. That you answered my question.
Oh, okay. Oh, okay, thank you. Yeah, I saw your hand up. All right, very cool. All right. Okay, so now I'm going to move on. Damn it. What is I'm doing wrong here? Okay. Here we go. We can do it like this. Nope, that's the wrong one. Here. Okay, now what you're looking at here, if we were going to make an amplifier, and we're in tube amps, 131 college, freshman year, and we want to make a lowest common denominator amp, like the very most basic amp you could possibly make. Well, if we did that, it would be a Champ Model F5F1 like this. This is a Fender Champ 5F1. This is your most basic amp that you can possibly make. Now, you remember when we first started this course, we talked about the four sections of an amp being the preamp, the output stage, the power supply, and the speaker. And in this situation, your preamp is here. See, here's your input jacks, and there's your gain stages. There's your preamp. And a preamp, what a preamp does is it amplifies pressure or voltage. It creates gain. Gain is voltage. Higher voltage is higher gain. Voltage is electronic pressure. You know, we were talking about the difference between voltage, high voltage, low voltage, high current, low current, you know, because you can have high pressure or low pressure, and then the current is like the volume of electrons that moves past a certain point. And so the output stage of this amp is very similar to the design of this preamp stage, although we are using only one tube and we're using a pentode instead of a triode, but it's still wired very similar. You still got your grid resistor, so you have a reference of how the grid is more positive or more negative to ground. You still have your bias resistor and your bias bypass cap, but instead of having the familiar 100K plate load resistor like you'd have over here on this plate and like you have over here on this plate, instead of having that, we have a transformer. And the reason why we have a transformer is because the impedance of a speaker is so low that you just can't couple it with a tube because the impedance of a tube is so high, and the impedance of a RC coupling is very high also. So you just can't couple that to a speaker. Now, if we look back, and then we have the speaker. So you've got all four parts of the amp. And here's the power supply down here. This is the power supply that's powering everything. And so there's your four parts: the power supply, the preamp, which amplifies voltage, the output stage, which amplifies current. And when you multiply voltage times current, you get wattage, which is what is needed to drive a low impedance speaker. So there's your four parts: speaker, output stage, preamp, power supply. Every amp you ever see is going to have these four component or four sections. Maybe the sections may not be the same. You know, maybe on the power supply, this right here is a full wave rectifier, tube full wave rectifier. We covered this last week. I'm going to go over it again. But basically, you could have that. You could have a bridge rectifier. You could have a half wave rectifier. but it's going to have some kind of power supply. Every amp is going to have a power supply because your tubes need high voltage, and the wall does not give you high voltage. The tubes need DC, and the walls give AC. So you've got to have a power supply, and this is the particular power supply that's used on this one is the full wave. Okay, and then you've got to have some kind of preamp. Now this one is just a simple preamp where you have the same, basically the same circuit we saw earlier. This circuit here, it's the same circuit, but it doesn't have the bypass cap. And when you don't have the bypass cap, you get a little less gain. You also get more compression. So this doesn't have the bypass cap. But this circuit here, you got your grid, you got your reference to ground through here, you've got your plate load resistor 100K, and then it's RC coupled to the next stage via this cap and that resistor. And then you have another circuit exactly like the first circuit here. You see this grid here, how it's going to this volume pot? It'd be just like this grid going to the jacks. And then this cathode goes to ground through a 1500 ohm biasing resistor. This cathode goes to ground, same way. This plate has a 100K plate resistor going to the power supply. This plate here, 100K plate resistor going to the power supply. So see, both of these circuits are identical. And then this circuit here is almost identical to that, the difference being that it's transformer coupled and it is a pentode. And we'll talk about why it's a pentode in a minute. But, you know, you've got your grid resistor going to ground, just like the others. You got your bias resistor, and this one has a bypass cap on it, just like the other. But the other would have a 100K plate load resistor because it's RC coupled. This one just goes through a transformer. And then the pentode, the reason behind the pentode, just real briefly, the original tube was a triode. But when they were trying to mess with it for radio and things that capacitance was an issue, they had too much capacitance between the plate and the grid. And so in order to increase that capacitance, I mean, not to increase it, but make it smaller, they had to move the plate physically far away from the grid. But then when they did that, they lost a lot of power, because the further you move that plate away from this cathode, the less power it's going to have. So in order to try to beef the power back up, they stuck another little screen in here. It's called a screen supply. Screen supply is the voltage that's supplying it. And what it does is it just has a real high voltage here, so that when the electrons see that, they jump towards that voltage. But since it's a screen with hardly any mass to it, and it's usually less voltage than the plate, they just go on through the screen and they hit this plate instead and go to the plate. And that way you're able to get quite a bit of amplification factor out of the tube. Now this one here is an output tube. And the difference between an output tube and a preamp tube is the geometry of the tube. The output tube has geometry such that it can handle lots of current, but the gain is not, the voltage gain is not an issue. The preamp tubes, on the other hand, are set up to handle lots of gain, but not lots of current. So, and it's because they're the size of the components inside and how far apart they are and all that sort of thing. The geometry of the tube, in short. So this is a 6v6. It's a power tube, draws a lot of current. It's a big tube. Okay. Now, I'm going to pause just for a second to see if anybody's got their hand up. Because if anybody has a question, they can go ahead and raise their hand, because I'm looking at the hands right now. Okay, no hands up. Okay, what I want to do now is I want to isolate this power supply, and I want to give you a new way of looking at your power supply. And this is basically the power supply right here. Okay, well, I was trying to get it where it kind of blocks out that other stuff. I'll tell you what, let's do this. I think I can copy that and just paste it onto a new deal. Let's see if I can just do that. Yeah, there you go. Okay, so let's look at this power supply. Okay, there are places in the amp that are grounded. Like the cathodes of all those tubes are grounded, you know, because the electrons come up through the cathode, they go through the tube, through the plate resistor, and back into the power supply. And they got the same thing over here, through the cathode, through the plate, through the plate load resistor, back to the power supply. And over here, through the cathode, through the tube, through the plate, back through the transformer, and back over here to the power supply. And of course, this one's the screen supply, and you'll have a little bit of leakage there. This is really not good to have very much screen current, but there is some. And so basically, all of these circuits are getting their electrons from ground. Now, how do they get to ground? Well, think of this power supply right here. I like to think of this power supply here as a pump. And what it's doing is, yeah, it's attracting electrons this way, but when they come in, they're being pumped back into that chassis. And then they're going to redistribute, because once they get back into the chassis, they go all over the place. Some of them will go over here to this circuit. Maybe some of them will go over here to this circuit. Some of them will go here to this circuit. And then that current goes back around through the rectifier circuit. Maybe this time it goes through here, but it ends up going back through ground, and it's pumped back into ground, and it goes back around. So that's how the current is actually flowing in an amp. Now think of these filter capacitors here. Think of these as batteries. They're batteries because they soak up extra electrons or give off extra electrons, depending. They don't want the voltage to change. As a matter of fact, that's one of the characteristics of a filter cap, is that it resists changes in voltage. It's like a flywheel for voltage. You know, whatever the voltage is on that cap, it wants to stay that same voltage. Just as if you had a battery that was that voltage. Let's say that this cap right here, it's a 450 volt cap, but we're not using 450 volts on it. Let's say there's 200 volts on here. You got 200 volts over here. Well, once that thing equilibriums to 200 volts, it wants to stay at 200 volts. It does not want to move. So if you have more or less current coming through this tube right here, there's a tube right there that I don't show, but it's there. As more or less current goes through here, it'll change the voltage on the plate of the tube, but it doesn't change the voltage here because you got this filter cap that's opposing any change in voltage. And then you have the same thing on these other circuits. You got one here that's feeding the transformer. And remember, this is pulsating DC right here. And so we want that pulsating DC, which is going to sound like a hum through a speaker. Pulsating DC is going to be 120 hertz. It's 60 out of the wall, but when you rectify it, it becomes 120. So instead of that 60 hertz, you hear the 120 hertz. And that's what you're going to have coming off of this rectifier tube. And so this filter cap right here takes that 120 hertz, which might look like this. Let's say this is 0, and you're going to have some DC. It's all going the same direction, but it's going to have 120 little humps in it. It's not like AC. See, AC would be this: positive, negative, positive, negative, positive, negative. It's not that. It's DC, but it's got a ripple in it. And that ripple is 120 hertz. And when you put a filter cap, put that onto a filter cap, it's like taking a big old flywheel and putting on that sucker. And then whatever the voltage is, it pretty much stays straight. You know, it's just nice and straight and smooth. And then, you know, then we have a resistor and then another one to keep it smooth and another one to keep it smooth. And think of these as being batteries that are feeding power to these various different tube circuits. In fact, in the old days, it would have been batteries. Think of it like it's a battery, and then this is like a charger. It's keeping the batteries charged up with positive voltage on this side. It's pumping electrons, negative electrons, into the chassis on this side. Okay. I'm going to pause for a second. Take a sip of my Mai Tai. Anybody got a question? Raise your hand. Okay, no questions. Okay, let's go back and let's look at this other, we'll look at this other drawing here. Oh, let's see, I got to do something different here. There we go. Okay, so we looked at the power supply, and then we looked at let's look at this input real quick. On this input, we really are only going to, let's say we're only going to use one of these inputs at a time. If you plug into the number one input, it will, when you plug in here, it's going to upset this ground, so you no longer have that ground. And so your pickup is connected through this 1 meg to ground, just like in this picture here. Be the 1 meg to ground, just like in that. But the difference is these 268Ks, this switch is still connected, so the 268Ks are now in parallel, and so you got a 34K in series with the 34K of resistance in series with this grid, because 268Ks in parallel make 34K. And we could draw that in here. It'd be like having a 34K here. Now, the 34K is not going to affect anything. Why? Because there's no current flowing through it. You do not have current flowing in this direction here. The only current's flowing from here to here. So since there's no current flowing through there, the resistor makes no difference whatsoever. What you're dealing with here is what's called a charge. And the charge is just going from positive to negative, but it's just a charge. So if this is positive right here, it's going to still be positive here because there's no current going through there. It's just a charge. If it's negative here, it'll be negative here. Now, and that's the way this would work if you plugged into the number one input. If you plugged into the number two input, however, a different scenario would occur. What would happen is this, if you plug into here, it's going to upset this switch, take that switch off, and this switch is still connected. So since this is connected to here, it's shorting this resistor out, and this point right here is the same as if it's grounded to right there. You can forget the resistor. The resistor's not even in the circuit anymore. This is just going to ground. So your guitar signal is going through this 68K, then it goes through this 68K to ground. And what happens, since you've got two resistors, the exact same value, and you're taking the signal off from between them, it cuts the gain in half. And in half is 3 dB. Now, why do they want to cut the gain in half? Well, here's why. When people were buying Fender amps, they weren't always buying Fender guitars. The Fender guitars had the single coil pickups. The Gibson guitars had the double coils, or if they had a single coil, they had those big soap bars that put out about 4 times what a regular single coil would. And so they wanted people to be able to buy their amps to use with other guitars. So they added this second input here, and that way if you've got a humbucking guitar and you're trying to get a pristine clean sound, you can plug into the number 2 input, cut some of the gain off the humbuckers, therefore it doesn't drive this front end as hard, and you get a cleaner sound. So that's why they had 2 inputs on it. Now this is just simply a volume control, and the way a volume control works is, up here you have voltage. Let's just say you have 10 volts right there of signal. And down here you've got 0 volts. Uh-oh, I did something wrong. Let's see. Let's try it again. Let's say you got 10 volts right here of AC signal. You got signal coming in. It's modulating this tube. Voltage is changing up here. It's making this change. Electrons are coming up and down to meet it. And it's working out. It's 10 volts AC. That's right here. If that's 10 volts AC here, and then this is ground, so this is 0 volts. So wherever this wiper moves is going to determine how much gain is being impressed upon this grid. Because if the volume is turned all the way up, it's going to be to over here, and you're going to get 10 volts on the grid. But if you turn the volume all the way down, then the wiper is going to be over here, and you're going to have 0 volts here, and it's going to turn this tube off. So that's how the volume control works. Turn it up, you're getting the full voltage. Turn it down, you're getting no voltage, and turn it anywhere in between, and you're getting a ratio, depending on wherever the wiper is, of somewhere between full voltage and no voltage. And then we're taking that same signal and we're putting it through another stage of gain, because we want to get the gain up high enough that it's going to drive this tube good here. And it works the same way as the other one. We're hitting this with gain. This works the same way. Your electrons are pumped into the chassis. They come up through here. They go through here, back around. Then when they get to here, it depends on which one of these happens to be positive at the time. Let's say this time it's this one. Goes back around at the speed of light. And every 60th of a second, this changes from plus on this side to plus on this side. Then when the current gets here, it goes this way and through the chassis and back around. But it's all going one direction, and it's having to go through this transformer. And a transformer is like a transmission or like a gear ratio, because you've got high impedance on this side. High impedance is going to mean low current. High impedance, you know, a lot of resistance, you're not going to have much current. That's high impedance. This side's low impedance. Low impedance is going to be lots of current. So we want to go from high voltage, low current to low voltage, high current. And the way to do that is with a transformer. And it's a step down transformer. And the ratio would depend on what speaker load you're going to use and what tube you're using and that sort of thing. But it can range, 2,000 ohms, 4,000 ohms. Could be 6,500 or 8,000. It really depends on what kind of speaker you're using. And now there's one other part in here that we didn't talk about, and it's this resistor here. This is our feedback resistor. What this does is, not all circuits are going to want to respond evenly over the frequency spectrum. And let's say there's certain frequencies that the amplifier just doesn't seem to want to do well on those frequencies. And then other frequencies it does extra well. It might be a little louder than some of the other notes. Well, in order to even things out a little bit, they've taken what's called a negative feedback. And what they're doing is taking a little bit of signal off the speaker, and they're injecting it somewhere back into the circuit where it's going to be opposite polarity of the speaker. And the reason they're doing this, when I say opposite polarity, let's say, here's one polarity. Let's say that you got a signal and it goes positive, negative, positive, negative. Well, the opposite polarity of that would be negative, positive, negative, positive. Same signal, but instead of starting off positive, it starts off negative, or vice versa. And so when you take these and you mix them together, you get nothing, because one is subtracting while the other's adding, and vice versa. So what they do is they take a very small signal, and it's limited with this 22K, and it's a very small signal. And we take that very small signal and we divide it down to very little, and we put it at a point in the circuit that it's out of phase with, or out of polarity with. And what happens is when the amp wants to do a note that's too loud, that note that's too loud is going to be fed back over here. And when it gets to this point, it's going to phase cancel that note some to where all of a sudden it's not too loud. So maybe it was too loud for, a millionth of a second, but, as soon as, speed of light, it corrected itself to where it's not too loud anymore. And then let's say you have a note that's not loud enough. It's not as loud as the other notes. Well, that note will have less signal coming back because it's not as loud as the others. And then once it goes to this resistor, it will have even less effect and less phase canceling. So basically this negative feedback circuit, the practical value of it is it helps to even out any of the holidays, so to speak, in your sound spectrum. Not all amps use a negative feedback, but a lot of them do. A lot of Fender amps do. A lot of amps use them. Marshall uses them. We use them on some of our designs. Some of them we don't. Fender used them on some they didn't. Okay, so anyway, these are the basics of a simple 5-watt amplifier. So I'm going to stop for a minute and see if anybody has any questions. Oh, I see one question here. What's the effect of using the wrong speaker load? Okay, we'll talk about that for a second. The transformer is wound to a specific turns ratio to match the transformer to the speaker load to the tube. If you use a speaker that is a different impedance, well then the ratio of the transformer will not change, but the fact that the speaker is a different impedance, it will change what this tube sees as a primary impedance. And that can affect it in a negative way, because if the speaker is smaller in value, let's say it's supposed to be an 8 ohm and you're using a 4 ohm, it's smaller in value, then that's going to make the primary smaller in value. And if the primary is too much smaller in value, then this tube is going to draw more current than it normally should, which is going to make it possibly do a premature failure, or certainly make it wear out quicker. It'll definitely make it wear out a lot quicker, because it's if you cut the impedance in half, it's like going from where the tube wants to be halfway between that and a direct short. On this amp right here, a 5F1. I believe this output impedance, I might be wrong on this, but I'm going to guess this is going to be close. It's normally 8,000 ohms, and it normally has a 4 ohm speaker. So let's say you decide you want to stick a 8 ohm speaker. Well, when you put that 8 ohm speaker on there, that transformer ratio doesn't change, so it's going to make the primary 16,000 ohms. And so now instead of this operating into a load that it can comfortably handle, it's trying to operate into a load that's twice. So it'd be like trying to drive up a hill in second gear. It could be done, but it's not optimum because the load is bigger than what the thing is geared for. Now, fender amps are pretty good about mismatching 100% either way. Let's say if you went with 2 ohm, if you had let's say a 410 speaker cabinet that was 2 ohm and you put that on there. Well, if you put to 2 ohms, then all of a sudden the primary impedance is going to change accordingly down to 4,000 ohms, and the 6V6 is running into a much smaller impedance than what it wants to see, and smaller impedance is closer to a direct short. Instead of, let's say if 8,000 ohms is here and a direct short is here, 4,000 is right there. It's halfway between 8,000 and the direct short. So it's going to draw more current like that. Actually, on the 16,000 ohms, it's not going to draw more current. It's going to draw less current because the 16,000 ohms, it's a bigger kink in the hose, so it's harder for the current to get through. The 4,000 ohms would be less of a kink in the hose, and that way it's easier for the current to get through. But on this, the 16,000, it's going to sound real compressed. It'll sound real compressed, probably overly compressed. And also, if you have the amp turned all the way up and it's a high-powered amp, and you're mismatching impedance like that, you run the risk of arcing a tube socket, because if you're trying to squeeze a whole bunch of current into that transformer, and the transformer, the resistance is too high, that current's got to go somewhere, and if it can't go through the transformer, it's going to arc on the tube socket. Okay, and then we had another question here. He says, so if I have a speaker that measures 6 ohms, should I just go with the closest output section? Well, here's the thing about that. 6 ohms would work. 6 ohms would work on an 8 ohm or a 4 ohm output jack. But when you have a transformer that's multi-tapped, usually in almost every case, the biggest tap is going to sound the best, because the biggest tap is going to be the whole transformer. Like say you had a transformer that was a multi-tap, it had a 16 ohm, 8 ohm, and a 4 ohm on it. The 16 ohm tap would be the entire transformer. So naturally that's going to sound better usually than using a portion of the transformer. Just like running an engine with all 8 spark plugs is going to work better than removing 2 of them. But you want to try to get the speaker load match, and you also want to try to use the biggest tap on your transformer if you can. Okay. How do you determine impedance from the type or quantity of output tubes? And what's meant by single-ended? Okay, on your output tubes, pretty much everybody uses a 4200 ohm primary for a pair of 6L6s. That would be a pair. A pair would be running in push-pull, which we haven't covered yet. This right here is your single-ended. And let me see if I can explain what that means. Okay, on a single-ended design, almost always you have one tube. Oh, heck, this thing's not straightening up. Let me see if I've got another drawing of it. I don't. Let's see here. Maybe this one. No, it's not doing. Okay, well, let's use your imagination because we're almost out of time anyway. The single-ended is just you have one tube, and it goes through one end of the transformer, and the other end of the transformer goes to the power supply. Now, since this is shown as a single-ended, all single-ended amps are Class A. And I'm not going to get into class right now, but just suffice it to say all single-ended amps are Class A. Push-pull amps can be either Class A or Class AB, but your single-ended is always Class A, and it's always Class A because there's always current flowing. It never cuts off, and the current's all going one direction. Now, you can have a dual output tube single-ended. We could take another 6V6, for instance, and just put it over here and just connect the plate of this one to the plate of the other one, the grid of this one to the grid of the other one, cathode of this one to the cathode of the other one, and the screen from this one to the screen of the other one, and still have it hooked up the same way, and you'd get a little bit more power out of it. It's not a very efficient way to do it because you could always go push-pull and you get way more efficiency, which is what everybody does. But I have seen some Gibson amps, some of the early vintage Gibson amps, where they'll use two output tubes and they just hook them in parallel and run it single-ended. Okay. Let's see. And then Mark wants to know if you have multiple taps wired to separate jacks, can you plug a speaker into each jack and run them all together at the same time? I don't know. It would depend on the amp. You know, some of these amps, they might have some sort of internal switching on the jack where if you plug something in, it switches it to a different winding. So I'm not sure about that. I know SVT does, Ampeg, and there's several other amps that have that where it switches to a different winding on your transformer. But if not, I guess you could run them all at the same time. You could just try it and see how you like it. Okay. That's about everything I have for tonight. If there's any other questions, though, I'll take one more before we... Here, I saw a hand. Jonathan. Talk to me, Jonathan.
Yeah, I emailed you about the filter caps value thing.
Oh yeah, and I have that. Matter of fact, I want to cover that real briefly. Let's do that.
Cool.
There was another person that emailed me too. I was saving that stuff for last.
Okay.
Let me see if I can find it. Yeah, I got it pulled up. Yeah, here it is. This is a question Jonathan had emailed me. He says, I wonder if you could answer a question regarding filter caps. I was thinking of asking it during the webinars. In the past, you've mentioned increasing the capacitance of the main filters and for the screen grid supply. My question is by how much? If I have an amp, say a Fender Hot Rod Deluxe or a PV Classic 30, which has 47 microfarad caps and 22 microfarad screen grid caps, how do I know how much to increase them, and can I increase them too much? Is there an optimum value, and if so, why don't amp designers, manufacturers install these in the first place? Okay, here's the deal. You can change the filter caps in an amp. This one is using a 16, 8, and an 8. You know, you can double them easily in most amps. For a 26L6 amp or a 2L84 amp, I have a 234 amp or even a 4. I like to use a total of 110 microfarads for this first one. And the way I came up with that is one day I was noticing I could hear the ripple current in the power supply when I'd play a B or a B flat, because you can hear it real good because it's right out of tune, because it's right in between the B and the B flat, so it's real easy to hear the ripple, especially on the 15th fret on the G string. So I was listening to that and I thought, I'm just going to keep adding capacitance to this till I don't hear that anymore. And I did, and it was 100 microfarads of capacitance. Well, you know, the tube manuals say don't do that, and because they don't want too much capacitance on these rectifier tubes. They're afraid it's going to make them arc. And so I thought, well, you know, I don't like that. sound, I'm just going to do it to my own amps and see how I like it. And if it arcs a tube or something, so be it. I just can't stand that out of tune sound. So I did that on my own amps. This was back in the early 90s. And man, it worked great. And I never had a problem with it. And so when people would start sending amps in from service, I would give them an option if they wanted to up the capacitance, and people would do it, and we did, and we never had a problem with it. But the tube manuals and everything will say don't do it. And there's a lot of people out there that build amps that have gone to training and stuff, unlike me, which I have not had any college training or anything like that, although I've spoken at colleges before about tube amps. But they'll tell you that I'm wrong and don't do it. And I don't care what you do. If you can do it or don't do it. I'm just telling you what I do. And if you want to do it, do it. If you increase the capacitance on the screen, what you're doing is just making that screen more stable. It's just going to give it a little bit more sting on the front end of the note, a little bit more definition on the front end of the note. That's all. You're not going to hear any dramatic difference. You have to even know what to listen for to hear the difference. But increasing it here on your main filter, the very first filter that hits your tubes, that's the one that's going to make it play in tune. And if you only have one tube like this, I'd probably use a 50 here, 50 at 500, But if it was a two tube, I'd either use 100 at 500, or I'd use two 220s at 350 and put them in series, so you end up with 110, but it makes the voltage rating go up. So, and that's called a totem pole stack, and I might do that. But anyway, does that answer your question?
Yeah, that's great.
Okay.
Yeah.
There was another question here. Oh yeah, also too, those 47s and 22s, those are made in Taiwan. Those are Taiwanese values. American caps will be either a 40 or a 50 or a 20 or a 30. They don't do those values. And by the way,
Right.
those are some horrible sounding caps. They need to come out of there anyway. Even a new one sounds bad. You get a brand new one, change the caps, you'll hear a world of difference. And if anybody needs caps, you need to talk to me about it. I mean, I'm not doing this to try to sell y'all caps, but I do have custom made caps, and they are very high quality, and they're a lot less money than the sprayed caps. So
I've got a bag of your 100 microfarad caps and your 40s. So I was thinking to put 100 in the place of the 47 and the 40 in the place of the 22.
Perfect.
Yeah.
That's exactly that's what I would do. That's what I would do if it was my amp. Okay, and then we had one more other question here. This was from Joe. Let me see if I can unmute Joe. Joe, to make it easy for me, can you raise your hand so I can find you on here? There's a bunch of people in here. I don't see your hand up. Okay, well, we'll save this for next week then. All right, so anyway, that's everything I have for tonight. I'm going to send everybody a link. I'm not going to send it tonight, though, because I've got a dinner date. I will send you a link, though, tomorrow.